Hello there and welcome back to part 7 of my algorithms video tutorial series. In this one we're going to make things a little bit more complicated. We're actually going to do the binary search. Obviously the binary search needs to work on sorted data, so we're going to need to have some sort of function to return a sorted list rather than just a random list. And also the binary search is best done with recursion, which is something that is beyond the scope of this tutorial to kind of explain. So I'll just basically go through the code. We can type it in together and we'll test it, and I'll show you how we test it to make sure that we know that it works. So rather than delete all of this test code that I've got, what I'm going to do is just highlight everything in Replit and press Control and then the question mark key, and that just comments everything out. That's a toggle, so if you highlight what you want again, press Control and the question mark, it'll untoggle the comments, so that way you can work on the code that you want. I'm going to write it inside of here, just so that we can get it working, and then we can move it into the utilities.py. So the first thing I'll really want to do is I'm going to look at getting the data and just make sure that we can actually get some data. So the way we're going to do this, I mean, we could do a function, but it's pretty easy to just create a list of a certain number of values. So if I say that the range 16, if we turn this into a list and we store it in data, if we print data, what we've actually got is we've got a list of all those values. So that's probably enough for having a sorted list, and it's certainly enough for testing it to make sure that it works. So we'll write the actual binary search function. I'm just going to call this binary search. Like before, we're going to pass the data list that we want, and I'm just going to pass in call a variable called value, which is the value that we're looking for. It's probably best that we put our code comment in, so let's just rather than me type it out, I'll just paste that in so that we see what we're doing. So the binary search, the way that this works is we're just going to, I want the size of this. Recursion works by finding base cases. So the base case for this function is if the data size, the size that we're given, is actually equal to 0. So one of the base cases will be that if this size value that we just worked out from the length of the array is equal to 0, then we want to return 0. So that will basically break out of the recursion and won't run anymore. The second base is that we've actually found it. So the base case for that would be that if the actual value that we're looking for, before we do that, we need to work out the central point. So I'll create a variable called half, and we'll make it equal to size, and I'm going to use the floor division, so the two divide signs, make sure that it's not like doesn't turn it into a floating point, so it'll be divided by 2, but it'll be a whole number. So once we have the half, we're going to say that if the value that's at that halfway point in our list, if it's actually equal to the value we're looking for, then we've won, and we'll say that it just took us that one check to return. The next part is where the magic happens. So this is where we'll actually call the value again. So what we basically want to do is, if the value we're looking for is less than the current value in the middle, the one that's at the center of this list, then we know we need to search the bottom half of the list for it. So the way you do that, we're actually going to, I know it is a little bit confusing, but we've already done one check, so we need to definitely have one, and then you run binary search again. So binary search, This time we're going to search in the bottom half. So the way you do that is we go from the start to half, and this is just called list slicing here. So that's kind of like another topic entirely. It's worth its own video, so I'll just leave that alone. The opposite of that is that then we need to search the other half. So if it's not less, then you know it's going to be greater than, so you've got to search the top half. And again, we'll just return 1 plus, and then we'll run the binary search again. This time the data we're looking for is the top half. So we'll go from half plus 1 up to the end of that list, and we're still looking for value. So I'll just add in a comment, search lower half here, and in here, this is where we're search again in upper half. It is a little bit confusing. What the fun part is just working out whether it actually worked or not. So I'm going to do a few little test pieces here as part of the video, just so that we can see that it actually works, and we'll see what the best case and the worst case are for any size of data set just by testing. So I'm hoping you've done the binary search and you know what the results should be. That's the best way that we can actually test this. One other way that we can test it is we'd actually print out the, when we're searching, we can actually print out the list that's been sent to the algorithm to search again, so that we can see that it's actually working. It's probably one of the best ways of doing it. It doesn't require it, but it definitely will help us to visualize what's happening. So I'm going to print the, I'm going to print this. This is the array. This is the leftover array that's going to be searched when we run the algorithm again. So I'm going to print that during the search for the bottom half, and I'm going to do the same for the search for the lower half, and we'll see what happens when we do it. So it's data square brackets, and then it's half plus 1 all the way to the end. So that's the top half. So by running this, if we just want to do a quick test, what we can do is we can say result equals, and then we'll do our binary search. We'll pass in the list data, and we'll look for what should be the central one. I think that's 8 should be the halfway point, using the floor divide there. So this should, in theory, if we print out result, this should print out 1, because it should find it first time. So let's run it, and you'll see we print the list first, so that's the actual list, and then it prints the value 1. So a floor divide works just by dividing it by 2, and kind of like if it's in the middle, it'll go up. So 8 was the central one, so we know that did work. With 16 items, if we half 16, the maximum number of times you can actually do it is 5. So if I wanted to do a different search, let's try maybe say it's not the 8, say it's maybe the 4. If we search for 4, we'll have a completely different result. So let's run here. So what happens is it prints out the original list. Then you see that it searches only the bottom half. So this is where it printed out the bottom half of the list. And because 4 was the central point, it found it, and it added 1 search onto the 1 from the return, which gave us 2. So it actually it only took 2. If we were to maybe do the central point of the next half, that would be like the 2. So we would expect a value of 3 if we search for 2 in this list, because it should take 3 checks. So let's run again, see what happens. So this time it took the main one, then it halved it again, then it halved it again, and it found it on this occasion because it was the 2 that we were looking for. The worst case scenario for this one should be like the 0. If we search for the 0, we should it's not the 2, we should half it, and then we'll have this one, and then it's not the 1, and then it should be the 0. So it will end up being like, is it 5? It should be. So if I search for 0, let's see what happens. So it's taking a little bit longer than normal. So I did actually finish, but so we've got the main one, and then it takes the bottom half, and then it takes the next bottom half, and then it takes the next bottom half, and then it takes the 0. So we end up with 1, 2, 3, 4, 5 potential comparisons, which I believe is correct. And so I'm fairly happy to say that this algorithm is what I'm looking for. It shouldn't ever be more than 5 for 16 elements. So the algorithm appears to work. I'm going to remove these prints. Feel free to leave them in if you really want to, but if you're going to do a huge amount of these, it might be a bit of an issue, a bit of a problem. So I'm just going to maybe just comment mine out, and then we can take this algorithm, this binary search here, we can Control X, pop it out, and put it into our utilities in here. Down here, pop it in. So we have our binary search in. Back to main.py. The important thing is any of the values that I want to use, any of the functions I want to use, I'll need to binary search. I'll need to include it in the imports. I will do CSVs eventually, but for now I don't need it. And then I don't need the randoms because I'm not importing a random list. One little extension that you might want to do is you maybe want to, you can use this single line to get a list of a certain size, or you could turn that into a function if you want a bit of a challenge. So you can get any value back as a list from any range. And then you'll need to try to see if you can generate some test code where you create your CSV by doing what we did with the last one. So just adapt the code that you see here. We want to maybe step up in 10, and we want to maybe go higher, because I would imagine if you look at the CSV for this, the values will be very, very, very low. Because as you know from binary search, if you double the size of the data, at maximum, you're going to only get one more search. So let's test that theory with our algorithm. So if I double it to 32, I'm still searching for the value 0. So this is still the worst case scenario. If I do this, I've only got one extra search on top of the one that I did. So let's double it one more time. We'll go up to 64. And again, worst case scenario is that 0, because we have to half all the way till we've got like one element left in the list. And again, it's only one search. You could keep going up, and you'll see that even with huge arrays, the number of searches that a binary search requires to find the element you're looking at is very tiny. And obviously, if you're doing random numbers, if you're getting a random value that you need to search inside of your list, the worst case scenario, the very small 7 here, that's the absolute worst. It might happen in one. So yeah, that's pretty much this video. We've done a heap already. This is probably the most complicated algorithm, and I don't really expect you to understand it, but please use this to help you to compare the previous linear search algorithm with the amazingly fast binary search algorithm.